5 minutes of homework questions, and then we'll get to the next segment.
Yeah. When you say, I got to like this step, I like turned in the key, and then like it gives me this. And you say to download that. How do you download this? Like how do you download the key? Like I turn in like my GPG file, and then it gives me my public key and my adversary key. And you say to download that, but I'm confused as like how to download it.
Well, you have the key. You're looking at it right now.
Yeah, and I say I back that up, but just like a text, but that's not like.
How's that not the key?
That is like, so that's it. That's like it. You're just saving it as a text file.
Yeah, save it as it doesn't matter. I mean, that is your key.
I thought this was supposed to be I thought it was supposed to be a GPG file or something.
It is. That's an ASCII number GPG file. Okay. Yes. So you can copy that down like to your computer. You can do file save as to save it as whatever you want. Okay. That should be good. Other questions?
You're trying to get someone to sign your key.
It's going to say
Two separate people.
Okay.
And they will sign you.
How do you know that they signed it?
They have to say it back, right?
Yes, they have to send your key back to you right there.
Is there a way to merge those two back together without
Yes. You import them into your GPG key ring and merge all the signatures you have into your key. You use, I think it's this thing that will show you all the signatures you got. Hey folks, do you want help on the homework or do you want to talk to each other? Thank you.
Is there a specific GDP command that will turn an armored file back into the whatever you call it, wise version of the file?
Why?
Because it's easier to get information from that version of the file.
You just import it and then you can export it however you want, right? So your key ring has all your keys. So when you import it, you take a key in and you can export it out.
Whatever you want.
Right, exactly. You can also use GPG to interrogate that key to tell you everything you need to know about that key.
Okay.
It's probably better than looking at it manually. Yeah.
So every key signature you get changes your public key.
It adds a new signature to your public key. It doesn't fundamentally change your key, right? What you have is your key, which is always the same. If your fingerprint change, that would be insane. But you have additional pieces of metadata where everybody attests that they trust and they've signed your key. Yeah, go ahead.
What does it mean by key rings?
What?
What does it mean by key rings?
Key rings? The key ring is just like a GPG concept of you can have as many keys as you want, right? So when you're on GPG, you can have as many keys that are your keys that you actually own. All the public keys that you import go into this long key ring. Yeah, just like the concept of literal like a ring of keys. Yeah.
Do you or the TAs have keys inside?
No. It's from other students in the class. That's part of the assignment description. Yeah, you actually have to talk to each other. Oh. Words, people. That's like on minute 20. That's all the questions. Yeah.
So, just so I understand, so for signing fake keys, if you're signing one fake key, you lose 10 points flat.
No, I didn't say that.
Okay.
10 points of your score are based on not signing fake keys.
Okay.
If you sign 0 fake keys, you are guaranteed 10 points.
Okay. And you sign, so like it's not like all or nothing.
Probably not.
So if you don't do the assignment at all, then you assign no fake keys and you get at least 10 points.
I have not had that happen. I guess technically yes, but yeah, I don't know. Don't put yourself in that situation. More questions? Yeah.
Does the server signature, does it have a user ID?
Yeah. I mean, there's a link on the submission, on the assignment description to the server's key. You should download that, so you can look at that, right? Import that into your key ring, so you can look at what the submission server's key is, so you can see all the things about it, the fingerprint, the username. I think it's something just like CSE 365
Given the public key, I'm
Yeah.
assuming that has the person ID.
Maybe, you tell me.
Okay, so we could technically get the public key and decrypt it to get the name and verify it's actually them.
Before you sign it, yes. Right, so you can download, you should be getting their public key, right? You import that into GPG. That doesn't mean anything. You have to actually take another step to sign their key, right? And it will show you everything, like key ID, name, email, all that stuff. It's up to you to verify that before signing it. Once you've signed it and then send it back to them, then that's on you. Yeah.
Can you unsign a key?
No. Yeah.
When someone sends the signed key back to you, how do you import just their signature? Or do you just override the whole thing?
It doesn't override it, it's smart, right? It just adds any new signatures that is present.
Okay, so just import it and it's smart enough to do all
Yep.
that.
Yep. All right, cool. Now let's move on to new stuff. So now we're going to talk about authentication. So what are these? So we've talked about in the past this concept of authorization and authentication. So what are the differences between these two concepts? Yeah, very back. Okay, so authentication is trying to verify somebody's identity, right? Trying to say who is this person, and authorization is what are they allowed to do on your system. So what are some types of authorization enforcement things that we've looked at? Yeah.
Like root permissions in Unix.
So like file system permissions in Unix or in Unix, yeah. What else? Yeah.
Access control lists.
Access control lists, discretionary access control, mandatory access control, originator, is it controlled access control or originator access control? Right, so you can think about these as, just like we said, answering these two questions of who are you, and not in like a philosophical sense, but more in the sense of what is your identity to the system, right? And authorization is what can you do. So this is the core ideas we should look at. Can you have one without the other?
Yeah.
Yes? What? So in what sense? Lots of yeses, not a lot of yes, yeah.
I mean, these are just like quick server steps. Like you could say someone is who they are, and you don't have to define what they do. And you could say someone can do like some specific thing to verify who they are.
Okay, so you could have a system that has authentication of knowing who is who, but not actually restricting what anybody can do, right? You can have a system that doesn't check who you are, but limits what people say they can do. I'll pose the question in a different way. Is any of these useful to securing a system on their own? No? Why? Why no?
Because it doesn't matter if you know who is authorized to do, or it doesn't matter if you have a list of who is authorized to do what, if anyone could be anyone on that list. And in the reverse, it doesn't matter if you know who they are if you don't know what they're allowed to do.
Yeah, they're not restricting what they're allowed to do in any sense. Who cares who they are? Maybe, although, you know, this breaks down slightly, right? You could, so something like, let's say Wikipedia. Can you do stuff to Wikipedia that doesn't require authentication? Is that breaking the security of Wikipedia? Are you all elite hackers? Because you can go to the edit page. Why is that different? Yeah.
Because someone afterwards like verifies the information you get.
Okay, maybe afterwards somebody verifies the information that you give. Yeah.
More sensitive pages and like lockdown.
Sensitive pages can be locked down by administrators, and you actually need to know who you authenticate an administrator. Yeah.
It's also like self-representing to some extent, because if you put some nonsense on there, someone else will probably change it.
Hopefully somebody will change it if you put nonsense on there. Any other thoughts? Yeah.
Technically, like authenticate through your IP address, so like they just block your IP address.
Yeah, so there actually is some form of authentication in the sense that they know your IP address. Your authorization is as a yes, right? So they're not authenticating your identity to the system, you're essentially a guest on the system. And I would also say they audit, right? So there's a log in the edit list of, even if not what person, what IP address at what time made what changes, so somebody could easily revert your changes, right? The other way to think about it is this is core functionality of Wikipedia. You don't have a wiki if everyone can't edit it, or at least in the Wikipedia side. Cool. All right, so we're going to study different types of authentication. We're going to look at kind of what that means and how we, so and before we get into kind of all these details here, what are some authentication systems that you're familiar with? Yeah.
Your username and password.
Your username and password for what? To what?
To send into like those websites like email or MIASU.
Yeah, okay, so let's use email, like Gmail, right? So why is your username and password important there? Yeah. So you can access accounts, but how do they know that those accounts are your accounts? Yeah.
In a perfect world, you would be the only one who has that password.
You would be the only one that knows that password? Why?
Because you created it.
You created it when you first created the account, right? So they're linking that account creation step, and on their side they create some account. And then later on when you try to access it, you can give them that same password that you originally had when you created this account. Cool. What other authentication systems? Yeah.
Some sites use like a 6-digit code that they'll send to your phone.
Yeah, so sometimes some sites may send codes that they send to your phone over SMS message. Yeah.
Token-based.
Token-based in what sense?
So the first time you log in, they give you a token that you send back and forth that confirms you're still that person.
Oh, interesting. Okay, so yeah, so you could log in once. They could, it's kind of, in some sense, generating you a unique next password every time you log in. They give you your next password. Next time you log in, you use that password. Then they give you a new password. What other styles? Yeah.
There's like biometric,
Biometrics, so fingerprints, right? Face recognition. Anybody have a phone that recognizes their face? Or a computer that recognizes your thumbprint? Right? These are all different ways of authenticating, trying to see who a user is. What about something like, how do you share, let's say, files on, well, yeah. So how can I share with you a file that's on my Dropbox? Yeah.
You send a link to my email, and you're assuming that that email is my email, and then nobody else has access to it, so that you know the person that is accessing it is me.
Right, so I can generate on Dropbox or any of these cloud systems a link to a file, and I can share that link, and anyone with that link can then now access this file. So I'm not necessarily authenticating who you are, but you can access this file with this link. Okay, cool. This makes sense. So, okay, so we are going to define some terms. So we first, in terms of talking about authentication, and this will allow us to compare and discuss different types of authentication systems. So we'll talk about password-based systems, two-factor authentication systems, all these different types of systems. So we have the principal, which is a unique entity, and an identity, which specifies a principal. So the key difference here is that a principal is the actual unique, whatever, entity. In this case, we're using entity. It could be a person, it could be a program, it could be a process, whatever. And the identity is inside the system, right? So you are who you are. When you're accessing your Gmail account, Gmail is linking your principal with their identity in your system of your email account. Does that make sense?
Can you explain the between identity and principal?
Yeah, so the key is in this internal representation, right? So each of you, think about, like, you all have an ASU ID. Are you that ID? Is that your person is an ID? What is that ID?
It's a representation of you within that system.
Yes, it's your representation inside ASU's system, right? It's just a unique number that uniquely identifies you in their system, right? right? So in that case, you, the person, are the principal. Your identity to ASU is your ASU ID. Similarly, same thing with, email accounts will have an identifier, all these kind of things, right? Some unique way for the system to identify you. Good. Okay, and we can have some kind of subject that acts on the system on behalf of the entity. We'll see more clearly how this works. And the key thing we're talking about here is authentication essentially binds an identity to a subject, right? So that says, okay, this user, so the subject here would be the user acts like your browser, right? Your browser, again, is not actually you. It's a software program that's running on your system. You access my ASU, right? And then the authentication system binds your identity, your ASU account, with your web browser, depending on the information that you give it and how it authenticates you. Does that make sense? Cool. Okay, and so we've talked about we've actually talked about a lot of different types of authentication systems here. So let's kind of break it down a little bit. So when we talk about a password, right? So what is a password actually checking? We're going to retread it a little bit. We talked about this briefly, yeah.
Something that you know or remember, or that only you should know or remember.
Right, so it's some secret value that only you should know, right? So a password should be a value that it's checking that you know something. So and this is different ways of thinking about different authentication mechanisms of something that you know. And there's kind of an implicit requirement here. Should it be your name? Should it be the name of the account?
No.
Why not?
Yeah.
Yeah, those aren't private information that only you know, right? So inherent in here is the something you know, comma, that nobody else knows. Right? And again, so why is a password, think about that, why is a password something that you know and other people don't? Yeah.
Because it's unique to you.
So it's unique to you, or why is it unique to you? Yeah.
Well, the decorum is that you don't share it with people. It's supposed to be secret.
Yeah, so you created it, right? Inside your brain, you created some password. You remembered it in your brain, and then later on they asked you about this piece of information, and if you haven't shared it with anyone, and nobody else has stolen your password after you typed it in or whatever, it's something that only you should know. Now, how does this break down?
Social engineering, if it's like something close to you.
Yeah, so social engineering, which is kind of the theme of your homework assignment, right? So if somebody tricks you into you giving them your password, I should have done this earlier. By the way, maybe I'll make a post on Piazza later too, but ground rules for the assignment. So no actual breaking into anybody's computer, no physical harm to anything. Okay? Set those ground rules, and everything else is fair game. All right? So don't commit any computer fraud, and don't commit any physical crimes or fraud. All right? All good? Okay, I'll repost this. Okay. Sorry, I forgot about that. Okay, so now think about those other ways that we talked about of authenticating to a system. So for instance, receiving a 6-digit code over text. What is that actually testing? Yeah. Yeah.
That you are who you say you are, that you're in possession of the phone number that you entered.
You're in possession of the phone number, right? It's not testing something that you know, right? Because this code, you don't know this code until you get the text message, right? But it's testing that you own a device that can receive text messages at a specific phone number. Yeah, you have something to add?
Does like fingerprint fall into that possession thing and stuff like that? Or like biometrics?
Almost. There's a bit of a difference there. We'll talk about that in a second, right? So, and this is kind of broadly this area of what do you possess? So what do you have, right? So that could be a phone. It may have two-factor authentication with my ASU. You use Duo on your phone. So what does that do? Somebody walk us through what happens. Yeah.
I mean, it'll just be like send push to your phone, you open the app, you refresh it, a little thing comes up saying, oh, a login request was sent to the computer, click it.
Right, so you log in on your computer, and then rather than a text message being sent, they send a push notification to your phone that you have to accept on your phone that allows you to log into the system, right? So this is testing something you possess. You possess a phone where you've already logged into the Duo app, which is not the website that you're logging into on that device. So it's testing that you actually possess the phone. What other things would be examples of things that you possess? Want somebody new? Just answer. Yeah.
Some government computers have a card.
Yeah, exactly. So government computers, you may need a key card. Also corporations. When I was at Microsoft, you had to use your key card to access the VPN. Yeah, I can't remember. Is it CSE? Is that the name of the systems?
Gotta grab your CAC.
Yeah, so your card. Also, anybody use two-factor authentication on Gmail?
Yeah.
Yes, well you should after this class. So I can show you here. So this is a bunch of randomly changing, this is the Google Authenticator app. It's a bunch of randomly changing codes. And I can freely share these to you because they update every minute, 30 seconds. And even if you have one of these, it's only valid for that 60 seconds. And a new one is generated that's completely different from this one. So similar of a UB keys or RSA keys, if you've ever seen those, that have randomly generated numbers. So you try to log in. Some banks have this, where you log in and you have to prove that you still have this physical device because there's some private secret data there that's shared between you and the bank that they can verify that that's actually that device. This is again verifying that it's something that you possess. I guess another example of this would be you can, it's actually kind of, well, can be a security vulnerability, but you can authenticate and unlock my computer by having my watch. So the watch will actually unlock the computer, so it's not authenticating me, right? It's not authenticating something I know, it's that I'm possessing this watch. Yeah.
So the Apple Watch don't you need like a password on the watch? So like you need to know the password for the watch.
You do, yes. So there's multiple things there, right? That way, if you can't just if you ripped off my watch and then tried to go and open my computer, because the watch auto locks when it's not on your wrist or when it detects that it's not on your wrist, I suppose you could cut off my arm and then quickly go, but I will just give you access to my computer if we're ever in that situation. Let's not take those measures. Okay, so what's the difference between, let's say, what you possess, right? Like a text message to your phone to prove that you have that phone number. What's the difference between that and your fingerprint? Yeah.
It's using something that you have versus something that you are. So like somebody else could take your phone, but they can't necessarily take your fingerprint, hopefully.
Yeah, or I think about it a different way rather than taking. I would say that the difference is in that can you change it, right? So can you change your fingerprint? I mean, you have 10 of them, but after 10, you're kind of, I don't know if toe prints work, but maybe those are a thing, right? So the other thing that we can think about is what are you? Like, what are factors of you, right, that are supposed to be unchangeable? So what are these types of things? So we talked about fingerprints. What else?
Retina.
Retina, so like a retina scan of your eye, which I've only ever seen those in movies, but allegedly they're real. I've heard they're real devices. What else? Yeah?
Your veins.
Your veins?
Yeah, they scan your whole hand and it's like an x-ray where they...
Whoa, that's good. Okay, veins or hand, I would say, maybe more generally, yeah. The structure of your face in terms of like the face recognition systems, right? Can you just easily change your face? I mean, you can, but it would be very, very expensive, right? It's more of a what you are than what you possess.
You ever seen the movie Face Off?
I have.
Just saying.
Yeah, so. And so this is another aspect, right? We can see how this compares. It's not something that you know. Your fingerprint is not something you know. If you can't just like, I don't know, write down your fingerprint, right? It's not a secret that only you know. It's something that you have that you can put on a fingerprint reader. Yeah.
So, what seems odd to me though is, I still feel like it could be something you possess because, for example, if someone were to take a copy of your fingerprint, like scan it into their system, they could easily make a replica of that fingerprint that would then work on fingerprint readers. Or, heck, the face scanners, or at least the ones on regular lower end stuff, you can hold a picture of the person up to it and that'll open it most of the time.
Right, so this gets into more, that's why I wanted to not do it on the, it's more about how easy is it to change it and get a new thing that you possess. Right, so with a phone, if I lose my phone or whatever, I can just get a new phone and say, this is now the phone I possess. And or a new YubiKey, those type of things, right? I can get new devices. I can't change who I am necessarily easily. And which becomes a problem if it's stolen, right? So if somebody steals your fingerprint, sure you can deactivate it and move to the other ones. And there's problems with all these methods. Like, you know, they try to do crazy things like, so to go off that analogy, they the first face authentication, you could just easily literally print out a picture of a person and just put it up to the screen, right? And then you could unlock their device and authenticate as them. They got around that by trying to do what's called liveness detection. So this is the whole area of how can you tell that that thing you're looking at is alive and not a fake piece of paper. So they developed this basically kind of looking at the eyes and seeing if there's movement. And so what they were able to do is you print out a picture of the person's face and you just put little black dots behind it and cut out the eyes, and then you move those black dots a little bit and it acts like the eyes moving and it logs them in. Or like, I think the iPhone now, I want to say does like 3D reconstruction of your face using some crazy sensors, right? So you can tell, it can tell the difference between a picture that you hold up and the actual person. But then I could take a picture of you and create, use a 3D printer to create a 3D version of your face. Yeah.
I know in the settings, like on iPhone 10 at least, like there's a setting you can toggle called like require attention or something.
Mm-hmm.
So it was like a security concern that you could just like hold the phone up to somebody's like sleeping.
Yeah, so the require attention is really cool because, yeah, so, and that's other bypasses, right? Of like making sure the person actually wants to unlock their phone. So that way you can't just hold the phone up to me and it will unlock. This was, I know, a problem in our lab when I did my PhD with fingerprint unlocks of phones. Somebody would fall asleep and you'd unlock their phone with their fingerprint. With the faces, so then the arms race to detect liveness of faces tried to look for the like blood vessels in your face to see if those would like pulsate, and that's what they kind of use for liveness detection. Of course, you can also fake this, so you can look up a bunch of cool research that's done on this kind of cat and mouse game of deciding for a computer system to decide if your face is alive or not. But for a lot of people, if the alternative is you either have a passcode on your phone or you don't, like you don't have any passcode where anyone can unlock it, or you have facial recognition where your phone is actually locked and encrypted, even if it's bypassable, it's probably still better, in my opinion. Okay, are these the only three things? So anytime you ever want to authenticate to a system, these would be the three things? Yeah.
I guess you could say like where you are.
Where you are, why?
I have the ASU two-factor authentication. I can have it remember like my work computer.
Okay, cool. So yeah, so you could, okay, that's an interesting version of where. So yeah, you could say where are you in terms of, has this subject authenticated before? Yeah.
There's with some credit cards that will let you make purchases in like different states, like if you're in California, it'll be like if you're in Arizona.
Right, exactly. So yeah, so your physical location could actually change your authentication. It could be where are you in terms of using a credit card? Yeah.
Like the GitLab for my work, if I try to go on it right now, it'll just like 404, you can't get there. But if you're on their network there, you can get it. I don't know how that works, but that's just how it works.
Yeah, so it could be different ways. It could be an internal IP address that's only accessible inside the company. It could be an external service that's limited by IP address. You have to whitelist specific IP addresses that are only visible there. Yeah.
If the last place you logged in was in Arizona, but the IP address matched to somewhere in like Eastern Europe, it's probably not the same person.
Yeah. So Gmail uses this. Anybody travel internationally and use Gmail, and it pops up like crazy warnings of like your machine's been used in whatever country you're in, and yeah, those are real things. Like, yeah.
Could you factor in like behavior? Like if you're using the credit card example, like what they're buying and stuff like that?
Yeah, okay, so behavior would kind of, I think I'd put that more under what you are, or maybe it would be more of a what you do. So you could do things, and people have done this, developing systems like with your phone. You could try to develop some kind of like fingerprint of how you type on your phone. And so you could tell if somebody else picks up your phone and starts typing, it's different. And so you could lock the device if they detect weird behavior. There's also, they've done things with phones and gait, like the way that you walk is relatively unique, so you can learn that from a person. So if somebody else picks up your phone while it's unlocked and starts walking away, it would automatically lock itself in that case. Yeah.
And there's like restriction now into like authenticating with your.
Louder? Sorry, I can't hear you.
There's like restriction now into like authenticating with your like brain signals. So like that's unique also, but it also like changes.
Yeah, isn't that sad if you wouldn't be able to? Not enough signals to unlock. Yeah, so I mean, kind of also what are you, right? Or what are you in terms of brain signals or EKGs or whatever kind of craziness, right? And so this is important for kind of multiple reasons. This is how in security, this is how we think about different types of authentication mechanisms, right? It probably falls into one of these buckets. And so we can start thinking about this in terms of, so what are some of the pros and cons of different types of things? So let's talk about, like, what are some of the benefits of what you know? You've been using passwords for years. You don't think there's any benefits? Yeah.
You never share your password, you know,
Yeah, so it's something that only you know, right? And so in the security sense, it should be very good in that nobody else should know this password, right? Yeah.
I like a little bit of a tangent, but how bad is it really to share passwords between things? Because like in my life, I mean, I've literally made like hundreds of passwords, and I don't make a new one every single time. I have a set of different ones that I use for different things.
Let's pause that, 'cause we'll talk about that eventually. Yeah.
I was gonna say, you have the power to share with other people. So like, I have an Amazon account, and we share the password.
Yeah, or Netflix, or any of those kinds of things, right? So a password, so can you share your fingerprint with somebody? No? Let's just say no. You can add somebody else's fingerprint as a way to authenticate to your account, but you can't fundamentally share your fingerprint with them and just clone it and give it to them, right? What about you possess? Again, similar thing. You can't physically both own the same device, right? It may be a shared device that you give them, whatever. So yeah, in that sense, there's a lot of benefit to a password that you can control who you share it with. Which is actually very similar to the key idea that we talked about a long time ago of getting into houses, right? It's like a key is nice, you can copy it, share it with people, but it has a lot of drawbacks. So what are some of the drawbacks then of what you know? Not passwords specifically, but yeah.
Usually passwords is something wants to create are going to be things that are easily rememberable.
Yeah, so the problem with, well, okay, so another way to say that is your password needs to be something that you can remember and that is difficult for other people to guess. Right? If my password was my name, that would be a very bad password because that's something that you could easily guess is my password. Yeah.
You could forget knowledge.
Yeah. Ooh, forgetting knowledge. Interesting. I won't make you do it, but a lot of people have asked me to reset their password on the submission site, right? So this is a very clear example. So some of you get passwords talking about how difficult it is to remember passwords or how you'll always remember your password forever and ever as your new passwords, yeah.
Kind of on that subject of like remembering, if you've got like a bunch of different passwords, you've likely gotten them written down somewhere, and so somebody accessing that.
Right, so then the counterexample, and this is this in Ferris Bueller's Day Off? No. what movie this is in. Is it Hackers? No. Can't remember. Anyways, but yeah, so the problem is, okay, so then you know if you forget your password, you can't access the system. So what do? You write it down somewhere. So if there was a sticky note on my laptop here that had the password for this computer, is that very secure? No, it's probably it could be better than, you know, I don't know, there's better than having a password, right? But still, probably not great because war games, that's the one that's that concept. Okay, there's a Matthew Bowers. Okay. Cool. Okay, what about what you possess? What are some pros and cons there? Yeah.
The clear pro is that you can't create your face, your fingerprint.
Oh, possess, not R. So possess would be device.
Oh yeah, well, I mean, if it's a device, you're a lot less likely to lose it.
Are you? You ever lost the phone? Anybody lost the phone?
Well, less likely than you would be to forget and integrate this.
Okay, yes, that's a fair critique, I'd say. Yeah.
And on the flip side, I can't give you my phone, so.
Right, it's hard to share. It would be hard to share in that sense. Yeah.
Sometimes you might not have the thing you use to authenticate with you.
Yeah, so you may be in a situation where you need to authenticate to the system, like you've either lost your phone, you've left it at home, whatever, yeah.
Would you say like what you possess would be like a key card in a way? So, and it's just like, say you're trying to get access into like different departments, you have this key card so you don't have to remember a password.
Right.
But the cons in that is something easily stolen.
Yeah, and if somebody steals it, that's all they need is that device to access the system, yeah.
Yeah, so like that, it has to have some sort of physical form. It's like, you know, and it's good if you write it down. If you don't write it down, there's no physical form that can just be stolen.
Right, so there's actually a really interesting dichotomy there, right? It's a physical device, I mean, somebody can steal it. But on the flip side of the password, if it's all in your mind, there's not always a way for somebody to steal that, although they can convince you to reveal your password, right?
If you're sharing a resource and it's like a physical key and you lose it, everyone has to like pay to replace their physical key.
Yeah, so, which actually I'd say is similar in some sense to a password, right? If you lost control of your password and had to change it, you'd have to tell everyone, but even worse, I think, in the terms of a key, right? If you lose it, like, oftentimes apartments may have like a key to the front door and then different keys for the individual doors, and if somebody loses the key to the front door, you have to rekey it, everyone gets a new key, it's a pain. Cool, okay. So, that was a good discussion. Let's move on a little bit and start thinking more formally about these systems. So we can think of an authentication system as some function or method. And again, here we're talking a bit abstractly. So we're going to talk about capital A is this some authentication information that proves somebody's identity on the system. C is some complementary information, so something that's stored on and used to validate that authentication information. So we'll see what this kind of looks like in real systems. F is a function that maps between them, so very simply, some kind of function that maps from authentication information to complementary information. L is the function that actually verifies the identity so that it takes in the authentication information, all of the complementary information, and then says true or false, so authenticate or not. And S is just some function that allows somebody to create or alter information. So this would be changing your password, all these kind of things. I know this is very, very abstract. Let's think of a simple password system where the passwords are stored in plain text. So what does it mean when I say the passwords are stored in plain text? Yeah.
You just open the file and read it, don't need to do anything to it.
Yeah, so you're writing the system. How would you write a system that authenticates you based on plain text? Yeah.
Assuming the password is stored in plain text, and you're writing in plain text, all you do is
Louder.
So if the password is stored in plain text, and you're keeping it in plain text, all you do is just compare are those two completely different.
Yeah, so you could all write this, right? An authentication system, that was a plain password, right? So you'd have to have some way to register new users, right? A new user to your system, you take a username password, you store that username password to a file, or append it to a file, and then when somebody logs in, you go through all the entries in your file and says, does this username and password match? If it does, good, you get access to the system. So we can model that using this framework we just showed. So here, so what would then be our authentication system? So what would be what would be the things that users authenticate with? Yeah.
Either username and password.
Yeah, username and password. We'll focus just on the password right now. So we'll say it's a set of strings that can be used for passwords, right? So have you ever tried to use a password on a service and it told you that you couldn't use those specific characters? Yeah, very annoying. This is actually very bad for security, but it happens. So then what's the complementary information? So what information is stored by the system in order to verify us? Yeah. The username and what else?
The set of all used passwords.
What was it?
The set of all passwords that have been used.
Yeah, so the set of all passwords, which is the same set, right? So this set, so all the strings that can be used with passwords are exactly the same as our complementary information. Okay. Okay, so F is not a bunch of different sets. We'll see why the set makes sense. We'll look at this this function F. So what's our test? So how do we test if a username and password is correct or the same? Yeah.
If the password given by the user equals the password in the database for that user.
Yeah, perfect. So it's just the equal function, right? Equality. We just want to see, are these strings exactly equal of what the user gave us as their password and what data we've stored in our system to check them. And we have some functions to set and change passwords. Okay, so what's the problem with this? Yeah.
If someone gets access to where you're storing those passwords, they'll know everyone's password.
Yeah, so where are you storing this password? Right, so let's say it's a website you're making, right?
On the server.
On the server, it has to be on the server, right? In order to check if people are who they say they are, all your passwords must be stored on a server. Can you guarantee that nobody else can ever get access to your system?
No.
No, this happens all the time, right? You can see even big companies, corporations, Chase, Equifax, Office of Personnel Management, all of these companies have had huge Target, credit card processing companies, Heartland payment systems. Anyways, there's a ton of these companies that have had breaches where people have had access to their systems and their servers. So then if all those passwords are stored in plain text, then when somebody breaks into your system, what can they get access to? Everything, right? Every single password. Okay, that takes care of a threat of somebody who is broken into our system. What other threats do we need to think about?
Guessing.
Yeah.
You trusting the administrator of the server?
Yeah, who else can get access? The administrator of the server, right? And do you want the administrator of the server to know all of your passwords? Thinking about going back a little bit, right? So what is that really a problem? I'll play the devil's advocate a little bit. Do we care if the administrator can see all of the usernames and passwords? They are the administrator of the system. They control the system. They can do whatever they want as any of these users. Yeah.
What if someone gets access to the administrator's account?
So somebody gets access. So now not only do we have to worry about people breaking into the server, but also the administrator's account. Yeah.
What if this isn't in a vacuum and the administrator, like you use the same password for two different systems?
Yeah. So now what if so does anybody use the same password on more than one site? I can't imagine there's not more hands. I'll wait. All decide to own up. Yes. Yes, right? So this means that, and let's say your usernames are email addresses, right? So I'm a malicious administrator. I go through all of my username passwords, my email addresses and passwords. What account do I want to get access to?
Email.
Bank account? I actually don't care about your bank account yet.
Email.
Email, why email?
So you get access to everything else.
Because I can get access to everything else through your reset password functionality on almost all of your sites, right? If I break into your email, I can get access to everything. I can, what people have done is they've set up filters to silently forward every email you get to their email account or to an email account they control, at which point you've completely lost control and secrecy of your email. So I can go through, I can see what are all the Gmail usernames in your account, I can see all the passwords, and I'll just try each of them. Is it likely that one of your users is reusing their Gmail password on this random site? Yes, it's probably very likely. Right? So this is a, and so this is another threat we need to consider is the threat of not just somebody breaking into the server, but an administrator or employee who goes rogue and has access to these data. Yeah.
On the same sort of note, you could have that with like, okay, you can say, oh, well, I trust that, Google is pretty secure, like probably people aren't going to be able to get into that, and they have a lot of safety precautions. But then on the flip side, if you reuse your Gmail password on a really weak site, somebody might be able to get into that site, get that password, and then go, oh, hey, I'm going to go try this password back at, their email, which is, as you said, more valuable than to reset everything.
Yeah, so we'll have a full discussion about that in a bit, but first I want us to realize that these threats exist, and then we can talk about ways to that users can kind of mitigate that. Yeah.
Oh, wouldn't this be really easy for man-in-the-middle attack?
Yeah, so another interesting thing is, so we talked about cryptography, right? The whole point is to keep the communication between two parties secret, right? So if there's somebody listening to you logging in with the username and password, then what can they do?
Use it.
Yeah, steal your username and password and log in as you. And does the system have any way to know that it's not you? No, because all they're using is your password. So this is why we looked at, it's actually why we looked at crypto before looking at authentication, so we could realize that we need some some cryptographically secure mechanism to talk to the other end. So this is why in the real world you want to make sure that you're logging in over HTTPS, basically always. Yeah.
What about verifying IP addresses?
Louder. So what about verifying IP addresses for what? Can you be more specific?
So if someone even takes your passwords, if they don't have the right IP address, then they still can't log in. I guess they still have your password, but
They might not be able to log in, although if they're, let's say, if they're in a position where they can man in the middle your traffic and there's in between you and the other system, it's highly likely that they can impersonate your IP address and log in as you. Or the way this usually works is rather than getting on the network in between you two, you downloaded some game or some game crack or something on your computer, and now they're on your physical device. So rather than stealing your username and password, sending it to somebody else, they'll just log in basically as you. It's even worse. You can even do things like they try to fingerprint browsers. So they try to, like websites will try to see what browser are you coming as, all this kind of extra security mechanisms. So sites that steal your browser information will then, sites that try to phish and steal your username and password will record all of that fingerprint information so they can recreate it later. The other way, sorry, and I'm going to keep going. The other way to think about, the other problem with IP addresses is how often is your IP address static?
Changes, we use Wi-Fi.
Yeah, so it changes when you use Wi-Fi, so think about your laptop, any mobile device like a laptop, a phone, these kind of things. Every time you connect to a new Wi-Fi network, it's going to have a different IP address, so you'd be logged out of all your services, so it's actually just a real inconvenience for people, so most sites don't do it. But if you want to have a really, you can do that to improve the assurance of your site. Yeah, that's a good point. Cool. Okay. Okay, then think about maybe like a system, like not necessarily, well, we talked about web. We can talk about a similar type of authentication system in terms of like a shared multi-user system, like a Unix-like system, right? You clearly wouldn't want all of the username password just in a file for everyone to read. That would clearly be bad. So, what's the solution here?
Add a better C.
Have a better C? Well, technically be a better F, I think. Yeah, or a better C works. Okay. So basically, the core problem, right, is the fact that we're storing in all of the passwords in plain text, right? So our complementary information is exactly the same as our authentication information. So we don't want to do that. So let's say we store nothing. How do we log people in? We can't. We need to store something, right? So what do we store? Encrypted. So encrypt. Okay, so take the password when they log in. Encrypt the password. Encrypt it with what?
Just do like some cipher on it that causes it to not be the original message, be some ciphertext.
Sure, but encrypt it on what? Like with what key? Yeah. The username? Okay. So take the username and password, use the username as a key to encrypt the password, store that. These are good. Let's okay. We'll call whatever. What do you want to use? AES? We'll use AES. So this is the key password. Okay, so, and then we store the username. Right, in our database. And so when they log in, what do we do? So they log in now with username and password. What do we do? Louder.
We compare to like the cipher, like the cipher that we have in the database and the cipher we just made.
Yeah, so I can recreate this, I can rerun this operation, I have the username they've given me, I have their password, I encrypt the password with the username, I create a cipher, and I compare it. If they're equal, I let them in. Okay, cool. So, now I've stored in my server everyone's username and cipher. Now you break into my server and steal all of it. Yeah.
Wait, isn't their username public? So why would you use it as a key?
So yes, let's think about that. So you steal all my username and ciphers. Can you steal everybody's password?
Yes.
Yeah.
Why?
Because use the key on the cipher.
Is what you use.
The username is the key, so you use the username to decrypt that cipher, and now you have everyone's password. You can do that for every individual user. Yeah.
Could you just store the cipher, like assuming a sufficiently unique enough encryption system to where you aren't going to have another combination of key or username and password that would come out to the same result? Could you then just store the cipher and just say, okay, does this combine to make one of these things?
Well, you need their identity, right? So your system has to have some way of saying, what is this user, right? So the username just maps the name that they give you to your internal identity of their user identifier.
Right. Okay.
So you need something, Spencer.
Should we, instead of using encryption, just use a hash to store the password?
So instead of encryption, use a hash. Well, let's pause that for a minute. Let's keep going with this encryption idea, right? Because the problem here is using the username as the key, right? Everyone agree? So what should we use as the key then? Yeah.
A password unique to the server, like the admin password?
Sure. Yeah. So let's generate some new key K, some random good key that we use. So now we use AES on the key K along with the password, and we get ciphertext, and we can store, now in our database we store a username shouldn't be able to easily decrypt the cipher because they don't have the key. The problem is in the situation, let's say somebody breaks into your server, has full access to everything that that server can access. What do they need to steal now? Yeah, they need to steal the list of username and ciphers and the key. And with those information, they can unlock everything. Also think about the administrator scenario, the administrator threat. So the administrator, does the administrator have access to the key K?
Yes.
For sure, the administrator has access to the key K. So they could decrypt all of these passwords and go backwards. And so you really not, it's in some sense better than just storing plain text passwords, but it has a lot of drawbacks. It still enables a lot of scenarios. So Spencer suggested we use hashing. So how does hashing help us here? So what would be my scheme? Yeah.
Well, since it's one way, you don't need a key.
So since it's one way, we don't need a key. So let's do, I'll write SHA here. We'll say I mean SHA 256. Okay, so now what do I hash?
Password.
The password. And then I get some output. What do I want to call this? I'll call it hpass. And then what I store in my database?
Pass and the hash algorithm.
Sure, let's say it's all the same. I'm always going to use SHA-256. Right? So now, so I store a bunch of usernames and the hash of their passwords. And now a user logs in, what do?
Hash their password.
Hash their password, check if that hash password equals this password. If it does, what do I know for, what do I know? Do I know that what they've given me is the password they gave me originally? No, why not?
It's collisions.
Yeah, it's possible that, I mean, there will be other inputs that hash to that same value. But because of the nature of hash functions that we talked about, it should be very difficult. They would need to try 2 to the 56th possibilities in order to find something that maps to the same hash value. Right? There's a lot. That's a lot of brute forcing. Yeah.
So I'm just wondering, would it be secure if you hash their password on the front end and then just send that without encryption over?
Yes. Let's we'll think about that for a second. Any other points I want to make here? Okay, so now let's go through this. So I have a bunch of usernames and hashed passwords on the server. So we'll go through the exact same threats we went through before. Somebody steals this list of usernames and hashed passwords. What do they know?
They know the username then, and then they know the hash for some hash. And so that what they can do is possibly just, go through a bunch of random algorithms and do hashing and try to guess what that password might be.
Yeah, okay, so they could try guessing passwords. Does anything stop them from guessing that my password is Adam, hashing Adam, and then seeing if my username matches that password?
Takes a while.
Right? There's nothing preventing them from doing that. They can do that. What about, let's say that you and I have the same password as password 1. Would you be able to tell who has the same password here?
Yeah.
Yeah, why? Yeah, they both hash the same value, so you'd actually be able to see who has the same password here. So it's actually making brute force fairly easy. You can brute force the list of common passwords, and you can check in this list what accounts have exactly that password. But it's still better than the other cases. Now there's no K to steal, right? The user's job is to brute force these username passwords. Okay, let's then change our situation a little bit to say that now client-side JavaScript, we SHA-256 the password, and then we pass to the server the hpass, right? Which then the server checks if it's in the database. How does that change things? chain strings. Yeah.
Then it's equivalent to just storing the passwords in plain text.
In what sense?
Because like what's being sent over the wire and what's being stored are the same.
Yeah, so it's an interesting thing. It doesn't, fundamentally it doesn't really get us anything. It's one of these things where it seems that it's better because instead of sending your password over the wire, you're sending now a hash version of your password. So nobody can go backwards to know your original password. But to authenticate to this website, they don't need your original password. What do they need? The hash of your password, which if you're sending this without encryption, they can just steal the hash of your password and log into the site as you without ever knowing your original password. So essentially you've turned your password into something that the server considers as your password. And so you gain nothing by this. So you still have to encrypt the communication scheme, and if that's your requirement, you might as well just give them your password.
Makes sense.
Yeah. Okay, so how do we get around this problem? Yeah, please.
Can you explain the whole thing about inside hashing again?
Sure. Okay. So the question was, we'll draw a little diagram. Right? So I have the client in all of these. So in all of these models, right, the client sends the server the password. Right? And then then the server has to validate, and not only does the client send the password, but also the user name and the password, right? So it has to tell them what account they're trying to log in as. But we can think of, let's say the server knows what user they're trying to log in as, doesn't really matter. Sends the password, right? What we said is, so anyone in the middle, right? So you have Eve here in the middle. Eve can now steal this password if they're able to see this communication. Right, so we talked about crypto. We know that we can create an encrypted communication channel between the client and the server, and this way Eve can no longer steal our password. Right, and this is why this public key infrastructure is so important, because the only way we can do this, if we haven't already shared an AES key with the server, is use public key crypto to send essentially first an AES key that we use to encrypt this communication, or whatever. But essentially we need to use public key crypto. This is why the client needs to know who the server is, which is why verifying domain names is so important. So you're not accidentally sending your password to an attacker's PayPal.com, you're sending it to the real PayPal.com. Yeah?
So how does the client side encryption, like, so are you saying it's worse than if you sent the normal password and you encrypted it?
No, so this was the scenario. Okay, so this was scenario 1. Scenario 2, the recommendation was hash the password and send it over the network to the server without any encryption. So the idea is, well, encrypting this communication channel is a pain. What if we just sent the hash of the password? Right? Because here it seems better, because now if Eve steals this, they can't get our original password. The problem is all they need to log in is our hash of our password. So at this point, Eve can steal the SHA of our password. Our password can be as insanely complicated as we want it to be, but Eve doesn't care. She has the hash of our password. She can log in by sending the hash of this password. So fundamentally, we'd still need encryption on this communication channel. Therefore, in most cases, if you got to build this anyways, you might as well do the first one. Yeah?
Are they equal, like, would they be equally the same, in and the same thing? Is there any reason to want to go on the client side?
It's a good question. Yeah.
I was going to say, if some person's listening to the incoming traffic on a server, when they see the, like, actually wait.
Yeah, so the benefit in some, it's very difficult because in some sense, right, if somebody's, even if you're hashing and your passwords are stored in best practices, right, so your database leaks and administrator can't see what all the passwords is, if somebody's on the server, they see every password that gets sent. Right, this was actually a major, Twitter had a problem, and So their database was storing passwords incorrectly when they were logging in, but by accident through debugging, they logged plaintext passwords to a log file. So you know so in this sense, it should be better because essentially they can't just simply see all the passwords. Like you're trying to hide the password, so only the user knows that password, so they should only send the hash. But this has problems. There are other schemes that you can do where the server sends a one-time random value to the client. The client hashes the password and the random value and then sends that back, and then the server can check, and that has better properties, so you can kind of get there. But in almost all cases, this adds a lot more communication, like a lot more complexity overhead, when really you should be thinking, if you're trying to authenticate, you need this channel, secure channel anyways, right? Because not only are you going to authenticate to the server, but presumably you want to do stuff to the server, and you want to protect your user's privacy by encrypting that communication anyways. Yeah.
It seems like beyond, like, even if both channels are encrypted, it's still better to not hash on the client side, because if you're hashing on the client side, then anyone who breaks into the server and steals those hashes can just log in directly.
Yeah, that's actually a good point.
Because then they can just bypass the client side logic of hashing and just send the hash directly to the server. But
Yeah.
in the other approach, it's going to be double hashing, so they won't equal.
Yeah.
I was gonna say, if you're hashing on the client side, or if you're hashing on the client side, then if the website has like a unique hash, versus if they stole the password, like we're assuming we're unencrypting it on the server side. If they stole the direct password after they unencrypted it, it's different than stealing a hash for that one website, because that hash probably wouldn't go to another website.
That actually, yeah, so that's interesting. That does impact the multi-website problem. So if somebody stole, in this sense, all the username passwords, they could log into this site as all of them, but can't log into other sites. There are some benefits, but yeah, the other thing is you need to change your client such that to make sure that it supports this, right? You have to verify that everyone, it just depends on how much control you have with the client.
What if you hash on both sides?
Hash.
So like you could store a hash of the hash.
It's the same thing as
I mean, it's still the same thing. It doesn't matter because fundamentally, if you take the hash of this password and hash it and compare it with this database, then I guess for the other passwords, you shouldn't be able to go back, but you still have to encrypt the communication channel anyways. So it's,
Oh yeah,
it's usually just better to put that complexity onto the server than a client. Yeah. You're trying to DOS me with your hashing questions. But what if we triple hash it first? What if we just remembered hashes of simple passwords?
What if you hash it logarithmically?
Yeah, stuff happens. I don't know.
What if we hash the hash function?
All right, so let's. Okay, so we still have this problem. So think about a shared system like a Unix server, right? So now we actually have a nice thing where we can store usernames and hashes. And we know that assuming we have a good hash function, it should be difficult to go backwards, right? From those hashes to passwords. But we still have this problem that if we both have the same password, then I can just, let's say, if I look at this list and I change my password to password, I can see everyone else who has the password of password, right? Because they all hash to the same value. Yeah.
So can't we just limit the set of A and make like unique, like more unique passwords by requiring like special characters or like other things?
Sure, it'll be password 1 and then exclamation point. So yes, we can try to make our passwords more, let's say sure we did that, but still it's going to be likely that some of us will choose the weakest possible passwords and we'll be able to see exactly what those passwords are. There's a hand here. Yeah. Retraction. Yeah.
So I've heard the term salting, like just to salt and hash your passwords, but I don't even know what that means. Does that address that?
Maybe. Depends on what it means.
Okay.
Yeah.
What if we add
store what hash function is used, which kind of goes back to your point of what hash function was used for these. Or another way to do it would be, so when the user creates their password, so we have, so the user is going, man, it's already morning. Time flies when we're having fun. Okay. So the user, okay, so the user logs in, so we have username, password, and we're going to generate some random data, we'll call it a salt. Go with our hash. Some random data, and what we store is we hash the salt and the password. This is our double bar, we're just appending it. Doesn't really matter how we combine it, but we need to combine it. We store that, so now we get the hash, I'll call it an SH, a salted hash of the password. And now what do we need to store in the database? The salted hash of the pass. And the salt. So let's say we don't. So let's say they log in, they give us username and password. So then how do I verify that this is correctly this user?
How's that self-generated?
Do that.
Randomly. It has to be randomly. Yeah. If it's predictable, not good. Right? So I need this salt in order to recreate and redo this hash. So the salt has to be part of the data that we store here. So I can take the shot of the salt and the password, and I can say, does this equal this? If so, yes, otherwise no. Right? And the key is that each salt is different. Now, if I have a password that's password, and you have a password that's password, the salted hash will actually be different. It also means, in an interesting way, so now if I'm going to guess, so if I have thousands of usernames, right? We said before, when we just had a hash, I could hash the password and just see every single user that has the username of password. Can I do that in this scheme? Why not? Yeah, because every user has a unique and different salt, which means I have to go through every user, use their salt, combine it with the password, hash it, and check if they have the username password. So now I'm at least requiring, and we'll talk about brute forcing later, but this is significantly better here. So we'll just go back real quick. Let's do this. So Unix even had this way back in the day. We'll talk about this later. But basically, so the hash, so it had strings of so you can actually only authenticate with passwords of 8 characters or less, which is kind of crazy. And then, so the idea was what we store is an 11-character hash of the password and a 2-character hash ID, in this case, essentially our salt is what we think about. And you can think about it in this sense, so there's 4,096 versions of modified DES that depended on the hash IDs. So this is the idea of having your salt change the hash function. And we have all of these nice things here. So yeah, so we can see, so basically we can ask the thing, hey, Alice wants to create a password called password. The Unix system will create that and then transform this password into the complementary information here. So here we have, and this is, we've seen this inside the etc password file. We looked at this a long time ago. We have the username Alice, and then here, I think these first 2 bytes are the salt, and the rest of this is the hash of the password. Cool. All right, so when we come back, 2